Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD heat transfer analysis, parametric study and optimization of a plate top heat exchanger using SolidWorks 2022. For understanding the geometry, we'll start from the assembly of this plate top heat exchanger itself. So without wasting time, let us start assembly. It is composed of one main plate and different types of gaskets are there, like backward gasket and forward gaskets. Let us select all the components one by one. This is known as backward gasket. This is forward gasket. And this is the front gasket. It can be applied at the back side also. This is the main plate. To understand the geometry, let us start with the main plate. So from this one, we'll provide hot water. It will flow in the forward direction. While moving in the forward direction, it is having some kind of space in the left hand side. So it will pass through this space, and at this side it will be closed. So having no way in the left hand side, it will come back in this position, and finally it will come out from this small opening, right? And you can see the back side also. Backside is completely different. You can see here, like from downside we'll provide cold water, and similarly at the back side of this one some kind of gasket will be provided. Let us make the initial assembly, then we'll try to explain the working principle, how it will be working, right? So in this assembly we have taken this one first. This one will be fixed. We need to make that component to be floating, and this one should be fixed, right? This is the main plate. So we need to create alternate hot and cold region, and that will be done using front gasket and backward gasket. This is known as front gasket and this is known as backward gasket, right? So initially what we'll do is this backward gasket will fix at the back side of this main plate. So right, and you need to select this one. This hole should be made with this hole. So green check, and this one will be moving back side. So you can select this side should be meeting this side. Two constraints are met, green check, and the third constraint, that is this face and this face should be parallel. Three constraints are met, so one assembly part is complete. In this case we need to provide one front gasket at the front of this one. This is the front gasket that we provided here. So again we can start assembly. That means this hole should be meeting with this hole. One constraint is met, right? Again this side should be meeting with this side. Done. Two constraints are met. Now the sides, this side should be meeting with this side. It should be parallel. Green check, all the constraints are met. So this part is done completely, right? Now we can analyze how this one will be working, right? See, now hot water will be passing from this top entry. It will go in the forward direction. By the same time, it is having some kind of space in the left hand side. It will pass through this path, and finally through this bone type of structure it will flow, and finally it will come down at this location. Now see the back side, what it is happening. Backside what is happening, from bottom side we will provide cold water. So cold water will be flowing in the forward direction, and again in this direction it will be closed. So cold water will be flowing this way, right? And finally it will be coming out from the top opening. So the thing is, cold water will be moving in the forward direction. By the same time it will move in this direction, right? So this place will be cold place and this place will be hot place. So at the two different sides of the main plate we are having two different heating zones. The front side of this one will be heated zone and the back side of this one will be cold zone, right? Now this is one assembly. Now what we'll do is we have to do the same type of assembly with different numbers of main plates and also these gaskets, right? That can be done using linear component pattern easily. So let us see this one in a different way. We'll see this one from side and we need to assemble these things. So remember this one, this is the back plate and this is the front plate. These two are different, not same, right? Okay. So what we'll do is we need to use linear component pattern, and initially we need to select the direction. Let us select the direction from here. It will go in the forward direction, so we can change the direction from here itself, right? Okay, fine. Initially 15 numbers of main plates you want to move in the forward direction. The thickness between these plates are equal to 20 millimeter. So from here to here it will be 40 millimeter. So 40 millimeter away we have to move this main plate. We want to make 15 numbers of main plates in the forward direction. Let us make the numbers 15 and the distance will be 40 millimeter. And the component to be patterned is this main plate. We have made this one. 15 numbers of main plates are provided at the front direction. Done. Next to that, what we'll do, we have to provide these different types of gaskets. The backward gasket and front gasket differently we have to apply, and the distance of this front gasket and the backward gasket will be different definitely. As this is the front one, so this one will be back. Alternately you have to move. So from here to here the distance will be equal to 80 millimeter. You can see this is actually 20 20 20 20. So distance from here to here will be 80 millimeter. 80 millimeter away we have to provide this backward gasket. Here about it will be approximately 7 to 8 numbers of gaskets to be provided for the back one. Again you can utilize linear component pattern, and we need to select the direction. Let us select the direction from here. You can change the direction from here. It will be in the forward direction. Now we need to select the component to be patterned. Component to be patterned this back one, and it will be at a distance of 80 millimeter, right? Numbers of this will be 8. Okay, so we have provided backward gasket at a distance of 80 millimeter, 8 numbers, right? Green check. So the back gaskets are provided. Next to that we need to provide the front gaskets. So we can see this is the back one. These are all are alternately we have provided back gaskets. This is the front one. Front one also by the same way we have to provide 80 millimeter away. So this gap should be filled up by front gaskets. So again you can utilize this one as linear component pattern, and direction you can provide from here itself. You can change the direction from here, changing the direction, and thing is components to be patterned is this front gasket, and that to be put at a distance of 80 millimeter, and the numbers of that one will be 8. Done. Green check. So this is the assembly. You can see this is the front plate, and hot water will be passing through this hole. It will go in the forward direction. By the same time it will be having some kind of space in the left hand side. It will move along this bones type structure, and finally it will come out from this small opening the downside. So this zone will be actually hot zone. At the same time exactly the back side of this one will be cold zone, right? Now to close this heat exchanger you have to provide some kind of front gasket and back gasket. This one is the front side front gasket. This is a different type actually that will be provided here itself, right? To close it you have to mate this one. So starting mate, and this hole should be mating with this hole. It's gone inside. One constraint is met. We can drag it from here. Now the thing is this face should be mating with the back face of this gasket, and also side should be parallel. Second constraint made. The third one is decode. This face should be mating with this face. It should be parallel. Done. It's complete in the front side. Exactly same way the back side of this one should be closed, right? So back side also will be having same type of gasket. So we can copy this same one. Now the thing is, this one we have to rotate. That can be done from here itself. Move component or rotate. Done. Right. Okay. For better understanding, what we'll do is we'll drag this one a little bit and show a better way. Let us drag it this one. Let us see the things. This is the back gasket, and this one should be mating with this face, right? So mate, can select this hole, should be mating with this hole. One constraint is met. Now the second one should be this face should be mating with this face. Second constraint is also met. Now the third one is required. That means the side should be parallel. So this side should be parallel with this side. Done. All the three constraints are met. So our assembly is ready. Go and check. Right. So this is our plate heat exchanger. What we have done is, in this plate heat exchanger, we'll be providing two different types of fluids. Maybe we'll consider this one water at different temperatures. From this top opening, we'll provide hot water at a temperature of 100 degrees centigrade. It will flow in the forward direction. By the same time, it will flow in the sidewise in the left hand side direction. And from bottom entry, we will provide cold water. It will flow in the forward direction. By the same time, it will move in the right direction. So in this case, you can see there will not be any direct mixing of two different fluids, but there will be transfer of heat between these two different fluids by convection, right? So our model is ready. We can save it by the name of plate heat exchanger, PHE. Save it. And what to do is, for starting the flow simulation analysis, first of all, we need to provide some kind of leads, because we need to provide a closed geometry, and for that we need to provide some leads at the openings, right? So tools, create leads. At the openings you can provide leads. These are the front openings. You can provide leads at this location. 4 leads are provided at the front location. At the back location also we can provide 4 leads. Selected. It is closed geometry. Now it is ready for simulation. Before that, we need to check whether the geometry is okay or not. That can be checked from here itself. Check geometry, and we need to check internal analysis. Let us check whether the model is okay or not. It is showing that status is successful, geometry is okay. Now you can see one thing. We can see the generated volume or fluid volume. Let us check it. This is the fluid volume. So our model is ready for simulation, right? So for starting this flow simulation, first of all, we need to initiate flow simulation environment, and that will be done using wizard. And we are keeping the name of the project as project 1. We need to select unit systems. It will be SI unit system, and from parameters we need to select temperature as degrees Celsius. Next to that, it will be an internal analysis, and from physical features it will be fluid flow with conduction. By the same time, gravity will be involved, as hot water has a tendency to go up. So we are considering gravity, and the direction of gravity is indicated by Y. You can see the direction of Y. It is indicating in the upward direction. Gravity direction will be along Y. It will be minus 9.81 meter per second square, and along Z it will be 0. Next to that, we need to select fluids. In this case, we are considering water, and we'll provide water at different temperatures from 2 different locations. So we need to select liquids, and it will be water. Next to that, we need to select materials. We are having 2 different types of materials. The main plate is made up of copper, and the gasket is made up of some high quality rubber. right? So you can select metals. It will be made up of copper, and the gasket will be selected during application of boundary conditions. Next to that, default outer wall thermal conditions are roughness we are considering, and finally thermodynamic parameters. Temperature will be 20 degrees centigrade and pressure will be 101.325 Pascal, and solid parameters also it will be 20 degrees centigrade. Let us finish it. You can see this is the computational domain. We need to hide this one, and next to that we need to select some fluid domains, because from two different locations we need to provide water at different temperatures. That domain should be defined. For defining that domain, let us have a segmented view of this model. We can cut it from specific planes. Let us cut the model from different planes. We can cut it from right plane, and let us drag it a little bit to see the location of the holes from which water will be passing at different temperatures, right? From this top opening we will provide water at a temperature of 100 degrees centigrade. So fluid subdomains, insert fluid subdomain. It will be water at a temperature of 100 degrees centigrade. You can provide from here itself, and it will be passing from this top opening. So this is the fluid subdomain for hot water at a temperature of 100 degrees centigrade, right? You can see. Green check. Next to that, we need to provide fluid subdomain for cold water. For that, again, we need to cut that model from other location. You can cut it and drag it a little bit inside to indicate the location of this cold zone. It will be passing from this hole, right? Cold water will be passing from this bottom entry, right? From here. So fluid subdomains, insert fluid subdomain, and water at a temperature of 20 degrees centigrade will be passing from this one. So this is the cold fluid domain. Green check. Done. Solid materials, we need to provide solid materials right now. For that, we can have a complete view of the model. This is our model, right? Okay, fine. So solid materials, insert solid materials, and predefined, it will be metals, copper. Can select all the main plates and green check. Done. Then you need to provide gaskets. Insert solid materials, and it will be made up of high quality rubber. In this case, we'll consider Teflon. So it will be made up of rubber. You can select polymers, and it will be Teflon. Let us select different gaskets. All the gaskets are made up of Teflon. This backward gasket, forward gasket, and also the front gasket, all are made up of Teflon. Excluding the main plate, all are made up of Teflon. Only the main plate is made up of copper. Green check. So materials are provided. Next to that, we need to select boundary conditions. And for providing boundary conditions, it is always suggested to have a segmented view of this model. Let us cut it from right plane and drag it a little bit. Done. So first of all, we'll provide hot water at a temperature of 100 degrees centigrade. And in this case, we're considering the velocity of hot water to be 0.1 meter per second, right? Okay. Let us rotate a little bit to select the location in a proper way. Boundary conditions, insert boundary condition. It will be inlet velocity of hot water at a temperature of 100 degrees centigrade, and velocity will be 0.1 meter per second. Thermodynamic parameters will be 100 degrees centigrade. From this one, we are providing hot water at a temperature of 100 degrees centigrade with a velocity of 0.1 meter per second. Green check. Now the downside, this one will be opening of hot water. So here it will be exit of hot water. So again, another boundary conditions, insert boundary condition. It will be environmental pressure or atmospheric pressure at the exit of hot water. You can select that location, green check, done. Two boundary conditions are applied. Next to that, you need to apply boundary conditions for the cold water, right? For that, what we'll do is we'll cut the model from specific planes again, and let us drag that cutting plane to the specific location, right? Green check, done. Now we need to provide another boundary conditions, insert boundary condition, and we need to have inlet velocity of water at a temperature of 20 degrees centigrade from this down location, and you can see the thermodynamic parameters. It will be 20 degrees centigrade from this down opening. Cold water will be passing at a velocity of 0.1 meter per second. Done. Now the opening of cold water is remaining. Opening of cold water, it will be having atmospheric pressure, so another boundary condition is needed. Boundary conditions, insert boundary condition, it will be atmospheric pressure at the exit of cold water. Green check, done. Now we can rename these things for our better understanding. First one, we can rename this one as inlet velocity of hot water. First one will be inlet velocity of hot water. We can rename this one HW, and this environmental pressure is environmental pressure for hot water. Similarly, for the down one, inlet velocity for cold water, it will be of cold water, and the last one, it will be environmental pressure for cold water. Boundary conditions are defined, right? Next to that, we need to select some goals, right? In this case, our main aim should be to see the temperature at the exit locations. By the same time, to have the efficiency or effectiveness of this plate type heat exchanger, we need to have LMTD, because among all the different types of heat exchangers, these plate type of heat exchangers are having higher efficiency, right? So we are having three different goals. Two goals will be surface goals, that will be the temperature at the exit surfaces of cold water and hot water, and the third one will be the LMTD, to find out effectiveness of this heat exchanger. LMTD, that is logarithmic mean temperature difference, that is the effectiveness of this heat exchanger, right? So we need to find out goals, and again for finding the goals, we need to have a segmented view of this model. We can cut it from specific planes. Actually, this is the inlet of cold water and this is the exit of cold water, right? So average temperature of fluid at the exit of cold water will be this one. This is average temperature of cold water at the exit location, and we can rename this one as average temperature of cold water at exit. Definitely it is a surface goal. Next one, we need to find another goal. For that, again we need to cut from specific plane. Done. In this case, we have provided hot water from top side, so downside will be the exit of hot water. So goals, insert surface goals, and we need to find average temperature of fluid at the exit of hot water. This is the location, green check, and we can rename this one as average temperature of hot water at exit. Done. And finally, you need to find out the effectiveness, that is LMTD, or logarithmic mean temperature difference, right? We can have the complete view of the model. This is our model, right? Okay, now the last goal, it will be our equation goal. Insert equation goal, and we need to find out LMTD, and that LMTD can be obtained from boundary conditions and from that surface goals also. Let us initiate with the bracket, and it will be obtained from boundary conditions, and let us add simulation parameters. Let us write the equation of LMTD. It is the temperature at the hot water inlet, that is equal to 100 degrees centigrade minus temperature at the cold water inlet, that is 20 degrees centigrade. Let us complete with the bracket, then minus, again initiate bracket, then it will be average temperature at the exit of hot water minus average temperature at the exit of cold water. That one will be obtained from the surface goes. It will be average temperature of hot water at exit minus average temperature of cold water at exit, bracket closed, divided by ln of the previous expression. Let us copy that one and you can paste it within ln, and here in this case, instead of this minus, it will be division. We can replace this one by division, accept this one with green check. So our equation goal is ready. We can rename this one as LMTD, or logarithmic mean temperature difference. This is actually effectiveness of this heat exchanger, right? All the goals are defined. Next to that, we need to run this one. Let us run this with new calculations. Let us run it. It will take some time. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. We can see the solver window from here itself. Let the iterations move on. Iterations are over. All our results are converged. You can see from here itself, like average temperature of cold water at exit is 47.98 degrees centigrade, and average temperature of hot water at exit is 72.26 degrees centigrade, and LMTD is 59.63. So we got all our results converged, right? Next to that, we'll see our results from different cut plots, and also we'll see dynamics of flow particles. Let us see the results from here itself. And first of all, we'll see cut plots. It will be temperature and pressure from different planes. And for seeing the dynamics of flow particles and also the different cut plots of pressure and temperature, let us make the model completely transparent. The model is completely transparent. Now you can see the different cut plots of pressure, temperature, and also the dynamics of flow particles very easily through these plates, right? First of all, we want to see temperature from different planes. So insert cut plots, and we're going to see temperature distribution, that is temperature of fluid through front plane, green check, right? So you can view this one from front side, and let us view this in the form of an animation. Cut plot 1, let us play. We can see different hot and cold zones are there. Alternately, you have created hot and cold zones. You can see here from the front side, from top end, you are providing hot water at a temperature of 100 degrees centigrade, right? And while it is flowing in the front direction, by the same time it is flowing in the left hand side, and in the downside also it is coming back, right? Similarly, from the other side, you can see we are providing cold water from downside at a temperature of 20 degrees centigrade, and it is moving in the forward direction. By the same time, it is moving in the right direction also. Triangular faces are actually different cold and hot regions. Cut plot clear and hide, and you want to see this from different planes. cut plot, edit definition, and we want to see it from right plane, right? Grain check, and we want to see these things from right plane, and we can view it from right side again. Let us play. You can see different zones are there. This is actually hot zone and this is cold zone. So alternately we're having hot and cold zones, right? Let us rotate a little bit. So you can see that there is no direct mixing of hot and cold water. By way of convection only, cold water is being warmed up and hot water is being cooled. Instead of this temperature distribution, you can see pressure distribution also. Let us see pressure distribution from here itself. So clear and hide, and instead of temperature you can see pressure distribution also. Grain check. You can see again downside we are having higher pressure and top side it is having less pressure. Let us play. Downside we are having higher pressure where temperature is little less, and top side where temperature is high, in that case we can see pressure is less, right? And in between we are having mixed zone with intermediate range of pressure. Let us view it from front plane. So clear and hide, and we want to see this from front plane. Edit definition, and we want to see it from front plane. This is pressure distribution from front plane. Let us play. Again it is clearly visible that at the bottom side we are having higher pressure and top side it is having less pressure, right? Let us clear and hide this one, and next to that we want to see surface plot. That means we want to see pressure distribution through the surface of this plate type heat exchanger. At the boundaries only we want to see pressure distribution and temperature distribution, right? Surface plots, insert surface plots, and we want to see temperature of fluid, and we'll use all phases, and instead of pressure will be temperature of fluid. Grain check. You see this is very important one. You can see from top side you are providing hot water at a temperature of 100 degrees centigrade. It is moving in the forward direction. By the same time it is moving in the left side. You can see it is moving along this triangular shaped path, and finally it is coming down, right? Now when this is moving in the front direction, by the same time we are providing cold water from downside. It is moving in the front direction. It is coming in the right direction also here, this one. So this part is actually a hot zone and this is cold zone. Alternately we are having hot and cold zone, right? And there is no direct mixing of hot and cold fluid, and in this case we can see by convection only cold water is getting heated and hot water is losing some heat. Let us clear and hide this one. Surface plot, clear and hide. Next to that we want to see the very important part, that is dynamics of flow particles. It will be obtained from flow trajectories. Insert flow trajectories, and instead of 20 numbers we want to make it 200 numbers of particles will be moving. Initially hot water was passing from this location. This is the lead. Select other. It will be lead number 24. Again you can select this one. Select other. It will be lead number 22. Again you can select the exit locations also. Select other. It is lead number 23, and finally the exit of cold water. Select other. It is lead number 21. Through these different leads we want to see dynamics of flow particles, and let us make the size of the flow particles to be 0.205 meter. Grain check. The particle study is being generated. It will take some time. Let us wait a bit. You can see the dynamics of flow particles. It will be better to see in the form of an animation. Let us see it from here. Flow trajectories. Let us play. It is clearly visible that hot water we are passing from this top entry, right? You can see it is moving in the forward direction, but at the same time it is moving in the sideways. Similarly, from downside you are providing cold water, it is moving in the forward direction, but at the same time it is moving in the right direction. In this case, we are not having any kind of direct mixing of fluids, right? Let us view this from front plane. See, we can see symmetric flow conditions from left hand side and right hand side. This is the hot plate, and we can see this is the cold plate. This is the cold zone, right? This is symmetric flow conditions are seen from this plate type heat exchanger. This is very efficient one. It is having higher efficiency, and effectiveness of this one is very high, right? Let us see this in a different way from asymmetric view. Let us see this one from right plane. This is clearly visible that we are having two different zones. This is hot zone, this is cold zone. Alternately, we are having hot and cold zones, right? So hot water is flowing in the front direction, and by the same time it is passing through the sidewise, and again it is coming the downward direction also, right? Let us rotate a little bit. Let us see this one in a different way. Flow trajectories, edit definition, clear and hide. Flow trajectories, edit definition, and arrow size will make it, instead of 10 we'll make it 5, and the distance is 20 millimeter. Let us see. Let us play this one. Flow trajectories. Let us play. You can view it from front side and also some side views also. From both sides you can see symmetric flow conditions are visible. This one is actually your hot zone, and this part is actually cold zone. Two alternate hot and cold zones have been created by using this plate type of heat exchanger. We can view it from side one also, right? Let us clear and hide. Next to that, we'll see our goal plots. We have already seen from the Solver window, but we want to see all these goal plots from Excel. So goal plots, insert goal plots, and we want to see all our goals from Excel. Let us export to Excel. First one, we can see LMTD. You can see after 127 numbers of iterations, LMTD is 59.63. Next one is average temperature of fluid at hot water exit. Initially hot water temperature was 100 degrees centigrade, and after 127 numbers of iterations, we can see the average temperature of hot water at exit is 72.26 degrees centigrade. Next one is average temperature of cooled water at exit. Initially cooled water at exit was 20 degrees centigrade, and after 127 numbers of iterations, average temperature of cooled water at exit is 47.98 degrees centigrade, right? Let us close it. Next to that, we need to go for some kind of parametric study, right? In this analysis, you could see that hot water has lost huge amount of heat, but at the same time cold water has gained huge amount of heat. Next to that, we'll go for some kind of parametric study. Suppose we want to go for some kind of optimization. If we want to get the temperature of hot water exit to be 75 degrees centigrade, what will be the mass flow rate or what will be the velocity of hot water or cold water, we don't know, right? To have an idea about the different conditions, initially we'll go for some kind of parametric study and we'll see at a different flow rate conditions or different inlet velocity of hot and cold water, we'll see what are the different results, right? So we'll go for some kind of parametric study. It will be obtained from here, solve new parametric study, and initially we'll perform one design of experiments and optimization. And in this case, we need to depend on input variables, and input variables will be obtained from boundary conditions. We can have a lot of input variables. We can vary the mass rate of hot water, cold water, and even we can vary the velocity also, or we can vary the temperature, right? Suppose you are considering the mass rate of cold water will vary, that is the velocity of cold water will vary. Initially in this case, we have considered velocity of both hot and cold water was 0.1 meter per second. In this case, we will vary the velocity of cold water, right? So boundary conditions, inlet velocity of cold water, we're considering this is as the input variable. We have to change this part, right? So velocity normal to phase we are considering as the input variable, and that to be changed. Initial value was 0.1. What we will do is we'll have a large range, so we'll consider from 0.01 meter per second to 10 meter per second. Green check, and we need to see output parameters, and output parameters are dependent on goals, and we are considering all the goals. That means average temperature of cold water at exit, average temperature of hot water at exit, LMTD. Let us see the scenario. Let us create the scenario with 5 numbers of experiments. Let us create it starting from 0.01. We can make it manually also, or it can be done automatically. Let us select the first one as 0.01 meter per second. Second, we are considering as 0.5 meter per second. Third experiment we are considering as 1 meter per second. Fourth experiment we are considering as 5 meter per second. And the last experiment we are considering the velocity of cold water as 10 meter per second. So with these different ranges of input velocity of cold water, we'll see what are the different goals obtained, right? So let us run it. It will take some time for getting the results. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis, right? The solver window has already started. Let the iterations move on. Iterations are over. Now we can see your results from design of experiments and optimization. In this parametric study, we have varied the velocity of cold water from 0.01 meter per second to 10 meter per second, but we have kept the velocity of hot water constant as before. It was 0.1 meter per second, right? So what we have done is we have varied the velocity of cold water from 0.01 meter per second to 10 meter per second. That means we have increased the velocity. As we have provided more velocity, so we have provided more cooling, and finally you can see that at a different velocities, when increasing the velocity, the temperature for both hot water and cold water is decreasing, and by the same time you can see the LMTD value is increasing, right? So from this parametric study you can see that when the velocity of cold water was 0.01 meter per second, in that case the temperature of hot water at exit was very high, it is 85.89 degrees centigrade, and when the velocity is 0.5 meter per second, in that case it is 64.56 degrees centigrade, and when velocity is 1 meter per second, in that case velocity of hot water at exit is 61.33 meter per second, and when the velocity is 5 meter per second, in that case you can see the temperature at the exit of hot water is 54.57 degrees centigrade, and finally when the velocity of cold water is 10 meter per second, in that case the temperature at the exit of hot water is 52.44 degrees centigrade. So from this data it is clearly evident that if we increase the velocity or mass flow rate of cold water, in that case the temperature of hot water exit will be decreased, right? Now from this parametric study we can see that if we want to optimize the temperature of hot water exit as 65 degrees centigrade, in that case the velocity of cold water we should range from 0.01 meter per second to 0.5 meter per second. In the next case we will optimize our result. That means we want to achieve the temperature of hot water exit to be 65 degrees centigrade. In that case we will vary the inlet velocity of cold water, and the range will be in between 0.5 to 0.01. Great check. Next to that, we'll go for some another optimization. So it will be new parametric study, and from here you have to select goal optimization, and for goal optimization you have to depend on input variables. Input variables will be obtained from simulation parameters, that is boundary conditions. Let us select boundary conditions from here, and in this case we are considering the velocity of cold water will be the input variable. Selected. Great check. And we're considering this one to be 0.1 to 0.5 meter per second, and the goal should be average temperature of hot water at exit, and we're trying to achieve the target as 65 degrees centigrade with a variation of plus minus 0.1 degree centigrade. Green check. Let us see the scenario and let us run it. Initially it will start iteration with 0.5 meter per second. In the next case it will start iterations at 0.1 meter per second. In this way it will try to minimize the gap and ultimately it will optimize. Let the iterations move on. Whenever it will be finished, we'll see the results and go for analysis. Right? Iterations are over and we can see that our solution is converged. At design point 4, we got our results converged. Initially you can see that when the inlet velocity of cooled water was 0.5 meter per second, then we could see the average temperature of hot water at exit is 64.45. At design point 2, when the inlet velocity of cooled water was 0.1 meter per second, in that case you can see the temperature at the exit of hot water is 72.2 degrees centigrade. At design point 3, when inlet velocity of cooled water is 0.472 meter per second, in that case the temperature at the exit of hot water is 64.679 degrees centigrade. And finally at design point 4, when the inlet velocity of cooled water is 0.4561 meter per second, in that case you can see that temperature at the exit of hot water is 64.94316 degrees centigrade. We got our result converged with a discrepancy of 0.0568, that is within our range, so our result is converged. Right? Let us close it. So with this one we'll conclude our analysis. This is a very simple analysis of a plate type heat exchanger. In this case we have done simple analysis, then parametric study, and finally optimization of a plate type heat exchanger. Right? Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.